Hello, so the purpose of this short video is to introduce Quicksort, the topic of lecture 32 of mcs360 Introduction to Data Structures. So we will introduce Quicksort with an example. So an example of a sequence of 10 numbers which we will sort in increasing order. So the sequence may look familiar. It's the same sequence we used with shell sort. So the idea of Quicksort is that we will partition the sequence in two halves, comparing to the pivot. So the pivot is the first element. So all elements in the first half of our partition are less than the pivot. In the second half, they are larger than the pivot. And we will do this by considering the elements one after the other, starting at this element, which, as you observe, is larger than the pivot. And we will also consider the last element. Now, I used a color red for the element at position with index up, and we have that everything that is up is actually less than the pivot. Everything that is less than the index up, so the index up here is at 1, this is index 0. Everything at left is less than the pivot, that is fine. And what we have here is the index that is called down, and everything larger than down, so further away from down, will be larger than the pivot. Now, it should also have said right from the beginning that Quicksort, the way we explain this here, is an in-place method, which means that we will write the sorted sequence at the place of the original sequence. So we will partition the sequence in two halves, but you see that this element 50 can actually not be in the first half of our partition because it is larger than the pivot. And that element cannot be in the second half because it is smaller than our pivot. Now, how can we solve this? Well, we can solve it by swapping 10 with 50. And then our index up increases and the index down decreases. So I'm indicating this with the colors of the elements on the position that is up and on the position down. Now 18 is actually at its right place. It belongs to the first half of the partition, so I leave it and I move the index up to the place of 31, also less than the pivot, and I stop increasing up when I hit the first element that is larger than the pivot. And then I turn my attention to the down index. Now down goes down, but observe the value of what is that down. 17 is actually less than the pivot. So 17 is actually belongs to the first half of the partition, not the second half. Well, how can I fix this? I can fix this by swapping 17 with 90. And then I know that everything that is here at the left is less than the pivot, and everything that is at the right is larger than the pivot. So 44 is still less than the pivot, so I can still advance up to 55. But 55 is larger than the pivot, so I cannot advance up anymore. 52 is larger, so it's in the second half, so I can actually move my index. And the way how I can indicate this, I'm not moving the value, but I'm moving the index. So 55 is colored twice because up is equal to down. And now I have reached the pivotal point in this partition. I know that everything that is at the right is larger than the pivot, and everything that is at the left of 55 is less than the pivot. So I can partition. I can partition by swapping 44 with the pivot. So I will swap at the place of 44, I will put 48 in black, that's the pivot. And then I have my element 44 that comes at the place of the pivot. So I have partitioned the sequence in a part that is less than the pivot and a part that is larger than the pivot. So if I'm now proceeding by sorting the first half and then sorting the second half, then I know that the sequence is sorted, because everything in the first half is less than the second half, everything in the second half is larger than the first half. So we'll play the same algorithm now, using again the first element as the pivot. Up is, there's the element 10, and down is the element 17. Now up is less than 44, so I can increase it once more, and then once more. So 17 is actually now colored twice. So I can no longer increase up because it has the value of down. Now with this example you actually see one of the worst cases that happens with Quicksort, when the largest element is the pivot or when the smallest element is the pivot. What we like is that the pivot actually fits in the middle, and then we have more or less equal halves. But here actually we have a case where only one element drops. Now in this case, so we are again at the pivotal moment, we would like to swap 17, but actually 17 is less than the pivot. So here actually we swapped 44 less than 48. We would be inclined to do the same here, but then actually we have a problem, because actually we have to only consider the previous element when this element here, where up equals down, is larger than the pivot. So what I will do is I will swap 17 with the pivot. So our pivot comes here, and I will copy. So now the sequence that we consider is the sequence of blue numbers. We went from 5 numbers to 4 numbers. So now the pivot is 17. And we continue our algorithm, advancing till we have the first element that is either equal to down or larger than the pivot. So we stop here at 18, then we look at down, and we can move down one step. So 18 here, I color it also green, is where up meets down. So here we have the case where again we have to swap the pivot with either up, but the place at up is actually larger than the pivot. So now actually we swap the element before that. So we will place the pivot at the place where 17 is. Then we have we swap it with 10, we have 18 and 31. So now we have splitted this sequence in a sequence of 1 and a sequence of 2 elements. And we are in the base case. So I hope this illustrates how the partitioning works and how actually the sequence gets sorted. So we are actually not done yet, but I think the case analysis should be clear that I can leave the second half as an exercise. So as always, the slides provide a completer picture, and there is of course the code that you should also consider.